Can machines think? You know, when the brilliant mathematician Alan Turing threw that famous question out there back in 1950, it wasn't just some abstract philosophical puzzle. It was literally the spark that would ignite the digital world we all live in today. For decades, the whole idea of a machine actually having human-like cognitive processes, well, that was just the stuff of science fiction. But today, we're not just imagining thinking machines. We're relying on them to drive our cars, diagnose our diseases, and even curate what we watch on TV. So welcome to this explainer. I am so thrilled to have you here, because today we are going to crack open the hood of artificial intelligence and look at the actual nuts and bolts making it all happen.
Okay, let's dive right into this. We're going to demystify machine learning by breaking it down into a framework that honestly makes perfect sense: the engine and the fuel. Just think of the algorithms, the complex math, as this high-performance engine. But as we all know, a fancy engine is completely useless without high-quality fuel to power the whole shebang. In the world of AI, that fuel is data. Throughout this explainer, we're going to see exactly how these two vital pieces interact to create systems that can learn, adapt, and make predictions without us humans having to hold their hands.
So here is a super quick roadmap for our journey today. First, what is machine learning? Then, how do machines actually learn? Next, we'll look at the fuel, ML data. We'll hit some real-world applications, and finally, we'll wrap up with ethics, bias, and limitations. All right, let's get into it.
Starting off with Section 1. What is machine learning? The paradigm shift.
To really wrap our heads around this massive shift, we kind of have to jump back in time to 1959. That's when IBM's Arthur Samuel realized something huge. He figured out that instead of telling a computer exactly what to do, step by step, we could build statistical algorithms that learn from data, generalize to unseen data, and, here's the kicker, perform tasks without being explicitly programmed. That last part, doing things without explicit manual programming, that is the absolute game changer.
Let's break that down a bit more. In traditional explicit programming, humans write all the exact rules. We give the computer the data, we hand over the rules, and it simply spits out the answers, right? Well, machine learning flips that entirely on its head. We give the computer the data and the answers, and the machine autonomously figures out the rules all on its own, and once it discovers those underlying patterns, it can apply them to completely new, totally unseen situations. It's wild.
Which brings us to Section 2. How do machines learn? The learning engine.
Just like you and I learn in different ways, the engine of machine learning actually processes information through three distinct paradigms. First up is supervised learning. Think of this sort of like a student studying with flashcards. The machine is fed data that is already labeled with the correct answers, like a bunch of pictures explicitly labeled cat, so it learns to map that input to the desired output. Second, we've got unsupervised learning. Here, the machine acts more like a detective. It's given massive amounts of unlabeled data and basically left to its own devices to find hidden structures, groupings, or weird anomalies. And finally, there's reinforcement learning. Picture a gamer trying to beat a really tough level. The algorithm learns by trial and error in a dynamic environment, earning rewards when it makes a good choice and tweaking its strategy when it totally fails.
Moving on to Section 3. The fuel, ML data, powering the algorithm.
So, as I mentioned earlier, an engine, no matter how brilliantly engineered, is really just a heavy piece of metal without the right fuel. In machine learning, that fuel is data, and it's processed in a very strict, disciplined pipeline. The data is split into three completely distinct phases: training data, validation data, and testing data. It is incredibly, absolutely crucial that these three data sets are kept strictly separate. Why? To make sure the machine isn't just regurgitating memorized answers, but is actually learning how to think.
Okay, let's walk through how this works. First, the training data is essentially the study phase. It's a massive labeled data set where the algorithm learns to identify those key patterns. But if we stop there, the machine might just memorize the training set, which is a huge problem known as overfitting. So we bring in the validation data. This acts like a progress check using unseen data. It gives us feedback to fine-tune the model's settings, what we call hyperparameters. Finally, once the model is all built and tuned, we hit it with the test data.
This is the final exam. It's typically unlabeled, simulating a true real-world environment, just to confirm if the algorithm actually works out there in the wild.
But listen, for this fuel to burn cleanly and actually generate accurate AI responses without underfitting or overfitting, the data absolutely must have three essential components. Number one, massive quantity. Just like humans, software needs a ton of exposure to become an expert. Number two, high quality. We're talking real-world multimodal data, text, images, voice, that mirrors exactly what the application is going to encounter when it's finally deployed. And number three, wide diversity. The dataset has to cover an incredibly broad spectrum of scenarios to make sure the AI doesn't develop dangerous blind spots.
So, Section 4, Real-World ML Applications, the road ahead.
All right, we've got the engine, and we've got the fuel. Where exactly is this vehicle driving us? Just look at the sheer breadth of what ML is solving right this second. It's powering the massive generative AI boom we're all living through right now. It's the engine behind your Netflix recommendations. Actually, fun fact, back in 2009, an ensemble machine learning model famously won a $1 million prize literally just for improving Netflix's algorithm by 10%. Crazy, right? Beyond entertainment, it's actively used in healthcare diagnostics to analyze medical images, in banking for real-time credit card fraud detection, and it is the literal brain inside those autonomous vehicles navigating our complex city streets.
Which brings us to our final stop, Section 5, Ethics, Bias, and Limitations, the bumps in the road.
Because this road ahead, it is definitely not entirely smooth. We're putting a ton of trust into systems that are, honestly, inherently vulnerable. I want to anchor this ethics discussion with a thought from the pioneering AI scientist Fei-Fei Li. She reminds us, and I quote, "There's nothing artificial about AI. It's inspired by people, it's created by people, and most importantly, it impacts people. That is a profound responsibility." It's just a really good reminder that despite all the incredibly complex math, human responsibility sits entirely behind the machine's wheel.
And those human creators have to constantly battle some major limitations. We talked about overfitting, which is when a model just memorizes the training data but fails completely in the real world. Then there's what we call the black box problem. This is where an algorithm's decision-making process gets so complex it becomes completely opaque. Like, even the original coders can't explain exactly why the AI made a certain choice. There are also adversarial vulnerabilities, where changing just a single pixel in an image can totally trick an autonomous vehicle's vision system. And perhaps the most critical bump in the road, algorithmic bias. Bias is a major roadblock. It happens when training data leads to discriminatory outcomes, which effectively digitizes our cultural prejudices. Remember, machine learning is just finding patterns in historical data. So if that historical data happens to contain human biases, whether that's in past hiring practices, healthcare disparities, or criminal justice records, the algorithm will just learn, adopt, and scale those exact same prejudices. It's basically the ultimate real-world example of garbage in, garbage out.
And a big reason these blind spots even exist in our data fuel is honestly just a lack of diversity among the engineers building the engines. Look at this number, 16.1. Globally, female faculty make up just 16.1% of AI researchers. And minority representation in new U.S. resident AI PhD graduates remains shockingly low. It just makes sense, right? When the people designing the systems don't fully reflect the diversity of the real world, the algorithms they build are probably going to struggle to serve that world fairly.
Look, machine learning is arguably the most powerful tool humanity has built in a generation. But, as we've seen today, its ability to think is entirely dependent on the data we feed it and the constraints we place upon it. So, I want to leave you with this final, kind of provocative thought to chew on. How are the invisible algorithms in your digital world shaping the biases you see every day? The next time a piece of software recommends a movie, approves a loan, or curates your news feed, remember the engine and the fuel working right beneath the surface. Thank you so much for joining me on this explainer, and hey, keep questioning the data around you.
Subscribe to Kinetic Prompt for more quality tech content.